Welcome back. Up to this point, we've been pretty much learning kinematics. Now I know I didn't use this word in class, but what kinematics means is just how things move. Meaning if an object is moving at a constant velocity, we can tell how far they go in a certain time. Likewise, we've been looking at objects that move with a constant acceleration. By just knowing some initial information, how far they went, what's their acceleration, are they accelerating, we can tell a lot about an object. That is known as kinematics. Kinematics is how things move. What I don't know is why do things move the way they do? Why do objects move with a constant velocity? Or why do some objects move with a constant acceleration? What causes an acceleration? And that is known as dynamics. Kinematics is how, dynamics is why. Before we move on to why do things move, we've got to define a couple of things first. The first thing that we need to define is a force. We can think of a force as a push or a pull. So anytime an object is being pushed or pulled, we know a force is being applied. But sometimes there are multiple forces acting on an object. There's multiple things pushing and pulling it. And that's where net force comes in. Net force is just the sum of all forces. So think of like your paycheck. Once you get a paycheck, you don't get all the money you earned. They take out taxes, Social Security, all that fun stuff, and then you're left with a net pay. That's all of your pay coming in minus all your pay going out is your net pay. Likewise, that's what net force is. It's adding up all the little forces to find one sum force. So now that we know what a force and what a net force are, let's talk about what inertia is. Inertia is this idea of resistance to change in motion. Inertia is also a measurement of mass. The more mass you have, the more inertia you have. Take this tennis ball. So it's pretty light, it's got low mass, so it has low inertia. Meaning my ability to change its motion is pretty easy. But if I take this bowling ball has much more mass. Meaning it has much more inertia. It's harder to change what it's already doing. Now we can talk about Newton's laws of motion. This is why do things move the way they do. Sir Isaac Newton came up with 3 laws that can apply to every object on why it moves the way it does. Minus the quantum world. That's way different and we won't get into that. Newton's first law deals with what happens when you have balanced forces, or when your net force is 0. That means if you take the sum of all the forces, they cancel each other out, so there is no net force acting on you. That's like thinking that the amount of money you get is all taken away. Your net paycheck is 0. Newton's first law says that if you have balanced forces acting on an object, meaning you don't have a net force, an object will continue doing what it's already doing. If the object is in motion, it will stay in motion. If the object is at rest, it will stay at rest. Newton's first law is sometimes known as the law of inertia. So that's what we talked about before, inertia. It's that resistance to change. And that's what Newton's first law means. Remember my tennis ball? We said my tennis ball has low mass, so it has low inertia. To change its motion is not that difficult. It has low inertia. It has low resistance to change in motion. Likewise, my bowling ball has much more inertia, meaning its resistance to change is even greater. So Newton's first law talks about when a net force is 0, objects will continue to do what they've been doing. But what happens when we do apply a force? That brings us to Newton's second law. So where Newton's first law talks about balanced forces, Newton's second law talks about unbalanced forces. This is where you do have a net force. So when you do apply a force to an object, it will begin to accelerate. It will begin to change its motion. But like we learned just a minute ago, some objects resist change in motion more than others. A tennis ball is way easier to move Then a bowling ball. Little mass, little inertia, big mass, big inertia. Little mass, little resistance to change in motion. Big mass, big resistance to change in motion. So Newton's second law says that if there is a net force acting on an object, then that net force is going to be equal to the mass times the acceleration of that object. What this is just saying is if you want objects to accelerate, if you want them to change their motion, then you have to apply a net force. What Newton's second law is saying is if I've got two objects with different masses and I want them to accelerate at the same rate, I need to apply more force to the bigger inertia object. And I don't need to apply such a big force to the smaller object or less inertia. Remember, inertia is just a measurement of mass. If you have more mass, you have more inertia, meaning it takes more net force to get this thing to accelerate. What you can also do is take this Newton's second law formula and solve it for acceleration. If this looks familiar, then that's good. That means you're looking at your equation sheet. In fact, right now, go ahead and take out your equation sheet. I'll wait. If you take out the equation sheet, we're still on the mechanics side. If you look at the fourth equation down, you see Newton's second law. You see it in a different form than this, but you see it as acceleration is equal to the net force over mass. So Newton's first law talks about what happens when you don't have a net force. Newton's second law talks about what happens when you do have a net force. And then Newton's third law also talks about when you do have a force. So not necessarily a net force. Newton's third law is saying that when you do actually have a force applied to an object, for every force that is applied, there's an equal and opposite opposing force. You might have heard the saying, for every action, there's an equal and opposite reaction. This comes from Newton's third law. This is Newton's third law. For every force you apply, there's an equal and opposite force right back at you. So for instance, if I push on the wall pushes back on me with the same amount of force that I push it. The thing about Newton's third law is that whenever you do have a force applied, there are two objects involved. So for instance, if I apply a force to the wall, there are two objects that are involved, the wall and me. When I apply a force into the wall applies a force back on me in the same amount of force in just the opposite direction. We use Newton's third law all the time, including when we're walking. When we walk, we push down on the ground and the ground pushes back up on us. The forces are equal, and when we push, I go forward, and then I push again, and I go forward again, and then I keep going, and then I keep pushing on the floor. The floor keeps pushing on me. And that's Newton's third law. Let's look more closely at a force. We know that a force is a push or a pull, and we know that the net force on an object is equal to its mass times its acceleration. So what unit do we measure force in? I'll just go ahead and tell you that the unit to describe force is known as a Newton. But a Newton is not fundamental, meaning other units make up a Newton. So what makes up a Newton? The SI unit for mass is kilograms. And the SI unit for acceleration is meters per second squared. So a Newton is just a kilogram times a meter per second squared. Don't get confused. When you're dealing with force, it's a Newton. A Newton is made up of kilograms times meters per second squared. If you ever forget, just remember Newton's second law. Newton's second law says net force is equal to mass times acceleration. If you know the SI unit to mass is kilograms, and you know the SI unit to acceleration is meters per second squared, then you can just multiply the two units together to get that a Newton is a kilogram times a meter per second squared. One thing to be careful on, force is a vector, meaning direction matters. Many times objects experience more than one force at a single time. So if you have an object with many different forces acting on it, it might be difficult to figure out what is the net force. So to help figure out what is the net force acting on an object, we're going to use what is called as a free body diagram, or an FBD. So a free body diagram is just a picture or a diagram that shows all the forces acting on an object. That's the important part, acting on the object. Acting on the object. Acting on the object. This is very important because Newton's third law says for every action there's an equal and opposite reaction. Many people want to draw the wrong forces due to Newton's third law. The point of an FBD is to show the net force acting on an object. To figure that out, we have to just look at forces on that object. We're going to try a very simple free body diagram. Whenever you do a free body diagram, you don't really want to draw the picture. That adds more problems to it. So whatever object you have, a ball, a person, a box, an airplane, whatever you have, draw the picture as a dot. So our object will always be a dot. That makes free body diagrams as easy as possible. This tennis ball is represented by that dot right there. What we want to do is we want to look at all the forces acting on this object. Remember, force is a vector, and vectors can be expressed as arrows. The direction of the arrow tells us the direction, and the size of the arrow tells us its magnitude. So if I wanted to look at the forces acting on this tennis ball at this point, I can draw arrows representing the force. Probably the most common force that you could probably think of that's acting on the ball is gravity. And we know that gravity points down. So here in the diagram on the FBD, I show that the force of gravity is pointing straight down. It has some sort of length, it has some sort of force acting on it. Now, there is one more force acting on this ball. We know that there is another force acting on this ball because if there was only gravity, it would fall. So what force is preventing it from falling? Oh yeah, my hand. My hand is pushing up on the ball. So now I can see that there's an equal sized arrow pointing in the opposite direction. We know it's an equal sized arrow because my object is not accelerating. It's staying right where it is. That means there are balanced forces, according to Newton's first law. For now, we're going to call the force pointing up just F. It's got a different name, but we'll get to that later. So there we go. We just learned about Newton's laws of motion. This explains why things move the way they do. So if you take these three laws, you can explain every action that is happening in the universe. From skydivers, to skiers, to snowboarders, to a planet crashing into another planet, to another planet flying away. So that's Newton's laws of motion. I'll see you in class.